Good morning. Agenda for today. What we're going to do today is density estimation. Primarily, I've got data, right? That's what we, so far in the classes, we were talking about data, whether data in terms of labeled data, where you have data points described in certain features with their labels given to you by a supervisor. This is called training data or labeled data. So which is primarily sampled from a distribution, say P x comma the label set. All right, primarily an element of y, you call it px comma y, is the distribution from which you get xy pairs, or else you have the unsupervised case where which is primarily the ones that we have seen is clustering. So you have samples from potentially a density called labeled as px, where you have got a lot of x labeled sampled from px. And in all these cases, the context is we have data sampled from an unknown density or a PDF. And how do you understand, how do you get a feel of the PDF from which you have got this data, right? Can you estimate the density from which this data is sampled from? And that's a question that we are going to address today. All right. And what you see on the screen is a histogram. All right. Have you heard of histograms? Say, for example, let's take a very simple example. You've got the marks obtained for a class, probably in university examination, and the maximum marks is, let's assume that's 100, and the minimum mark that somebody scored is 6, right? So you've got your entire class of 70 people to have marks from the number 6 up to 100. All right, somebody got 100 or so, let's assume that. And I want to find, or I want to rather draw a histogram around the marks. What do you do? While drawing a histogram, I'm sure you must have done that in your basic course in math. You will create bins of, let's assume that the bins are of fixed length. And then what you do is you will count, right? In each of the bins, you'll count the number of points falling in. We have got 70 people. Let's assume that the bins are defined as the interval 0 to 10 is one bin, 11 to 20 is another bin, 21 to 30 is other bin, and likewise 91 to 100 becomes the last bin. So how many bins you have got? You have got 10 bins, right? Now I can take the marks of every student in the class of 70 people, and I can put them in the appropriate bin. If somebody got somebody got 35 marks, that person falls into the bin defined from 31 to 40. All right. Likewise, I can count the number of people falling in each of these bins. And now what I do, I'll represent. I need to represent. All right. I can represent the frequency count of each of these bins, and that representation is called a histogram. All right. So I can say, like, okay, the bin, the x-axis, I can put the bins, and the y-axis, I can put the frequency counts, typically in the typical context. And I would say the bin 0 to 10, there are 3 people, so I get 3 represented there. So the y-axis will have 3 represented somehow, probably in the form of a chart, right? Bar chart typically. And then you will look at each of the other bins right from there, and then you get a distribution of the number of points falling in each of the bins, which is essentially, and once you have created this kind of a chart or histogram, you can see two histograms here, right? A histogram with what do you call, some 6 points are mapped onto, and they've divided into bins. And instead of what do you call, the counts, here what we have done is like what do you call, we'll it's essentially like they look at the number of points, and you add a
Sir?
small, hello, can you see
Yeah,
the screen?
the presentation is zoomed in, so we're just seeing the upper. Yeah, thank you.
Oh, okay, okay. Can you see it now?
Yes.
Okay, okay. So all I want to say is, you can mute probably. Okay. So all I want to say is, while you have represent the histogram, what you essentially get is a distribution, is a feel of your distribution of points. All right. And in the case of a discrete random variable, you have the notion of a PMF, or in the case of continuous random variable, you have the notion of a density function. Whatever be the case, the notion of distribution, or even what do you call them, the notion of distribution of points around the range of value that you have is an interesting concept. And histogram is a very naive form of representation. And if you look at a histogram, say for example, I've told you about a particular binning strategy for your marks. We have taken bin sizes of 10 marks each, right? 0 to 10 becomes 1, and likewise I can draw a histogram. I get some curve, and I can what I can do is I can increase the bin size to 20. What will happen is, like, I'll get maybe more points, but you have uh, again what do you call, you get some numbers, essentially the count, and you draw a histogram. And other entities, I can, instead of from 0 to 10, I can meaning 10 mark values falling into one bin. Rather, I can reduce the size of the bin. I can say like a bin size is 5, which means that I'll have fewer number of points falling in each of the bins. And I just wanted to ask you one simple question. If I keep on increasing the bin size versus I keep on reducing the bin size, where do you get a smoother curve? With a large bin size or a smaller bin size? One of you can unmute and answer.
A smaller bin size.
A smaller, right? So with a smaller bin size, but if you reduce the bin size to a single value, you essentially plot, right? Essentially plot the, you get everybody one, right? I mean, ideally, or a little more than that, right? You are fitting your data perfectly. All right, you may not be one, because there may be like values repeated. So everybody, like every point is represented. That's the extreme end. Other end is, you have a very chaos bin, which is every value is in one bin. You have only one bin versus uh, the number of bins equal to the number of unique values. So these are the two extremes, but we would love to have a value which is in between, and you draw a curve primarily based on the count you get on the bin, and you can even normalize those values. And what you essentially get is a feel of your distribution of values, right? And you have one form of representing distribution. Then you can talk about what do you call, a new point, either representative from that set also, or a point which is away from that set. Primarily, like if some point is what do you call, is very frequent, which is not as observed in a particular histogram, you say, okay, it doesn't seems to avoid the kind of distribution that I've seen in the past, right? So you see that most of the people were around, for example, around mark 60, the what do you call, the bin 61 to 70, and you were seeing the peaking of your histogram around the bin 61 to 70, and then you see that I got another 20 points. Most of it is around 30, which is like which at that point it will say, hey, I don't see like 30 had 30 been 31 to 40 had only 3 points, but this particular with this new point, the new set of points, what we call considered, that is changing the way the distribution is, may not be these points. If that is not a part of the data from which I have learned the distribution, I would say these set of points doesn't seems to be a part of this distribution, right? That's what the essential idea of a distribution is all about, right? So I just wanted to start from something that is very familiar to you. So essentially, histogram is a very simple technique where you can represent distribution of values. And so the question that we have in front of you is, you've got data sampled from a particular density, right? And is there any way in which I can identify, I can find out what is that density would be, right? And that problem is called density estimation problem. And there are primarily two classes of approaches around this density estimation. And the approaches are, it's very natural to think through these approaches, primarily because there is enough of sense around it. The first approach says, yeah, I know that these values are sampled from a normal distribution, or this is the result of in Bernoulli trials. And I know that these are obtained from a binomial distribution, all right? So the first class of density estimation techniques assumes that I know the structure of the distribution, the form of the distribution is known to me, all right? I would say the samples, the points, I know like this is px is normal, all right? It's a multivariate normal or a univariate normal, and this is normal. So the normal distribution is typically represented by two parameters. What are those parameters? Normal distribution will have a mean around which the distribution will peak, and a standard deviation, primarily a measure of spread. All right. So normal distribution, I know that my data points are sampled from a normal distribution, but I don't know which normal. I don't know the parameters of the model. And these kind of approaches are typically called parametric approaches. Parametric meaning I know the structure, but I don't know the parameters, right? Parametric model of density estimation is one class of density estimation, and the primary method works around parametric method of density estimation is called maximum likelihood estimate. We are going to see that today. There's another class. There's another class of density estimation techniques, which talks about, which says that I don't have any idea what the distribution is. I don't know the structure. I don't know what the distribution is. If that is the case, how do you estimate the density, right? How do you identify what is a density probability PDF from which you samples were generated, right? And from your basic understanding so far on counting, right, frequency-based methods to measure the notion of, or measure the concept of probability measures, you must have seen counting is an interesting aspect, right? So the second class of method for density estimation, one is I know the structure of the distribution, let me estimate the parameters of the distribution, the parametric. And the second class is I don't know anything. So these techniques are called non-parametric technique. The way in which these techniques proceed is by counting. All right, we'll come to the details of the method. Counting is I can count in two ways. I have a set of values. I can fix a small area or a container, right? And in that range of or the area over which this particular values are distributed, I can take my measurement cup or whatever, I call that the measurement container, and I have a fixed size measurement container. This for your understanding. I have a fixed size measurement container. I can put the measurement container at every consecutive point, and I can count the number of points falling into that measurement container. That's one way of doing it. And our approach, the approach that is mentioned in your syllabus, Parson window, is one such mechanism, which primarily estimate the density by counting within a fixed size container. All right. And the second, there is another variant to it, which is saying, hey, let me not look at a fixed size container, rather let me look at area which covers as many, like, given number of points. I'd say, okay, let me get into the data space and then count the area covered by 5 points. Let me count how many how much of space is needed to cover 7 points, because my count is, I need to look, like, if 7 points are found in a small enough area, I would say, like, it's a dense region. If 7 points are found in a what do you call, little larger area, like, I would say it's lesser in density, right? The density is basically the spread is more. All right. Or if the area is big, I would say 7 points. I need to get 7 points. I need to explore. I need to look at a larger area. I would say larger volume rather. I would say area is primarily like 2D. It's basically like if uh, I have to look at a larger volume to get 7 points. I'll say, like, okay, this is the density. The distribution is more, meaning the values are it's not a very dense, it's more of a chaos area, and the density estimate would give me lower values, right? These are the two approaches. Let me do a recap. To do density estimation is essentially identification that PDF. All right. To do that, you have two approaches. One is, I know the form of the density. All right. That's one. So I know that the data is coming from a normal distribution. My problem reduces to that of finding out the parameters of the normal distribution. And the second approach is, I don't know anything about the distribution. And in that, there are primarily two kinds of approaches. The first one being, let me take a fixed size container or a fixed volume and then count the number of points there and then estimate the density with that kind of a concept. And the second approach is, let me not do that. Let me fix the number of points and find out how much of an area is required for those 7 points to lie, which is the other end. So the first approach, in the non-parametric approach, where I don't know anything about the distribution, is called Parson window, where I have a fixed sized window over which I look at the density, I estimate the density. And the second approach, where I fix the number of points and then I look at how these number of points are distributed in the context of that particular problem. That approach is called K nearest neighbor based approach for density estimation, right? I'll give you a gist of both, and I'll concentrate mostly around the topic that we have as a part of the course, which is MLE, a maximum likelihood estimate, which is a parametric approach. And I'll also give you details on Parson windows, but K nearest neighbor algorithm is very similar, and I'll give you pointers to that also, right? That's what we're going to see today, right? Maximum likelihood estimate. This was just to give you an intro on what we do and why do we do this maximum likelihood estimation. And I would suggest all of you to keep a piece of paper, right? We're going to see some exercises now, and I will be just completing these two topics and formally today, and maybe like discuss, if we have more time, we'll discuss a few intro sessions to the next classes, but otherwise we'll be sticking on the maximum likelihood estimation and Parson windows for density estimation today, right? Let me maximize these slides. Maximum likelihood estimate is a general method for estimating the parameters in a model. You know that your data comes from a given distribution where you don't know, right, the parameters of the model. Introduced around in 1912 by Fisher, right? You can read about him. An estimation of model parameters that makes observed data the most likely. This is a statement. All right. Hello.
So it's again zoomed in. We can only see the top right.
Is it true for everybody? Is it true for everybody? Because it's basically like
No, sir. It's fine for me.
just check whether your screen is zoomed in. Just see whether you have a problem at your end. I don't see like it's a max screen thing. Let me play to the full screen. Is it better now? Can you read my screen?
Yes, sir.
Yes, sir.
Okay, that's good. Okay, thank you. And let's go ahead. So maximum likelihood estimate. The first step in maximum. Can you mute your mic? Can you mute your mic? This is pretty straightforward. I just want you to understand the basics. So the first step is likelihood. What is likelihood? Likelihood is likelihood of observing the data given if these were the parameters. Let's assume that your data comes from a given distribution. You don't know the parameters of the distribution. That's the context. That is where we'll apply maximum likelihood estimate. All right. You will estimate the parameters in such a way that the observed data is most likely. So you will write the likelihood function L theta, where theta is the parameter set. Theta will become more concrete very soon. Theta is the parameter set, and you want to make sure that probability of observing the data given theta, right? If theta were the parameters, the data that you have in hand is most likely, right? You want to estimate the parameters in such a way that the data that you have in hand is the most likely one. That gives the name maximum likelihood estimate. Let's see some concrete examples, then your life will be easier. We'll come back to this slide. Example, let's look at, you take a piece of paper. You have a piece of paper with you, all of you? Okay. Suppose you are flipping a coin 11 times and counting the number of times the head appears. This is your data. What is your experiment? Your experiment is flipping a coin 11 times, right, and counting the number of times the head appears. Let me repeat. Your experiment is flipping a coin 11 times and counting the number of times the head appears. Right? What comes out is your data. Right? What comes out, you will get some heads and some tails, right? And your agenda is counting the number of head. So your data is, you may see that you got 5 heads out of 11, 6 heads out of 11, 2 heads out of 11, whatever, right? That becomes your data, right? There are 11. If you look at this experiment, flipping a coin is nothing but a Bernoulli trial. There are 2 outcomes, right? With a probability of for a success event. The success in your case, we have defined that as the head turns up, the head appears, right? Let's assume that the probability is P. Counting the number of trials in N, in our case 11, independent. Let's assume that the trials are independent. These are independent. These are independent Bernoulli trials. The counting the number of successes, right, in 11 or n consecutive Bernoulli trials can be represented by a binomial distribution, right? That's a definition of, that's how a binomial distribution is typically used. Number of successes in n consecutive Bernoulli trials. That's one way of looking at a binomial distribution. All right, let us look at how do you estimate the parameters of P. So now, what is the current context? We know that the number of times head appears, which can be very well represented by a binomial distribution with a parameter P. I don't know the P. I don't know the parameter P. That's a context. All right. Find the maximum likelihood estimate for the probability P. All right. Using binomial distribution, the first step that you do in maximum likelihood estimate is you need to write the likelihood function. What is likelihood function? Your parameter P is the theta here. In our earlier example, like the first step is you write the likelihood function in maximum likelihood estimate. Your parameter, you have only one parameter P, so that becomes your theta. So you write the likelihood in terms of what is observed, right? you want to represent the probability of 6 sets turn up given the parameter p, right? Let's write the likelihood function in terms of the probability p, which is the probability measure for the success, which is essentially a head turns up in a trial, right? From binomial distribution, what is that probability of 6 heads turns up given p would be, can be represented as 11 to 6 into p6 into 1 minus p raised to 5. So this is trivial. This is a definition of a binomial distribution, right? 11 to 6, p raised to 6, 1 minus p raised to 5. That's what it is. And what is our agenda? Our agenda is to estimate p in such a way that what is observed, our data says that in 11 trials, 6 sets came up, right? What should be p, which will give me 6 sets turning up in a trial of 11 flip of coins, right? That's what it is. How do you do this? What is the definition of maximum likelihood? Estimate the parameters in such a way that the observed data is most likely. Our observed data is 6 heads turning up in 11 flips of the coin, right? And you have represented the likelihood function, and you know that this is nothing but binomial distribution, but I don't know the parameters of the distribution. How do you do this? Maximum likelihood estimate. We need to find the estimate of p that maximizes the likelihood that is the value of p for which observed data is most likely. I want all of you to spend 1 minute in reading the first sentence. We need to find an estimate of p that maximizes the likelihood. We need to find an estimate of the parameter p that maximizes the likelihood. That is the value of p for which the observed data is most likely. How do you do this? It's a maximization problem, right? This can be done by taking the derivative of the likelihood function with respect to p and equating it to 0. So the first order condition. So what you do is you have written the likelihood function, you compute dou LP by dou P and equate that to 0. So dou by dou P of probability of 6 sets up given P will be dou by dP of 11 to 6, P raised to 6, 1 minus P raised to 5. Equate to 0. Can you do this? Do that in a piece of paper and tell me the answer. Just do that in a piece of paper. Try it out. You can write this down if you have not copied it, just copy it. So now we know, like, we have observed data which is 11 heads turning up in 6 heads turning up in 11 trials in a coin toss experiment, and from that data, like, I know that the data comes from a binomial distribution, and how do you estimate the parameters of this binomial distribution? Right, that's a problem, and this is basically maximum likelihood estimate. I want to estimate in such a way that the likelihood function is maximized. All right, the likelihood function is maximized. This is a very straightforward computation. And how do you maximize this? You maximize, and primarily, like, if you apply the first order condition, right, and then you say, like, equate to 0, and then you take the derivative with respect to p and equate to 0. You get the value. All right, I'm just having, so you will end up like this. 11 to 6 is immaterial here. So 6p raised to 5 into 1 minus p raised to 5 is equal to 5p raised to 6 into, that's what you will get. And 6 into 1 minus p will be 5p, and 11p is equal to 6, and p cap, which is an estimate of p, would be 6 by 11 will be equal to 0.5455. Have you understood this? Just spend a little time. The steps are pretty straightforward. Maximum likelihood estimate. You need to write the likelihood function, all right, and maximize the likelihood function. And typically, you don't maximize the likelihood function straight away. For computational efficiency, you typically go for logarithmic representation of likelihood function and then maximize it. So you want to maximize the likelihood function so that your observed data is maximum likely given the parameter set. That's what it is. You want to find the set of parameters in such a way that your observed data is the most likely one, right? That is the definition of maximum likelihood estimation. Any questions on it? Any questions? All you do is you write the likelihood function and then try to maximize it. Try to maximize the parameters such a way that your observed data is most likely. We are going to see more examples and I'll give you an assignment also in this particular context. I want you to go back, look at. Can you mute? Can you mute?
Yes, sir.
Yes.
Sir, why do we calculate this? What is the need of calculating the estimation?
Density estimation. Where does this data come from? How do you know that which distribution give you the data? That's what it is. Density estimation problem is that. That's where I started. Right? Density estimation is all about identification of the distribution. Why doesn't it arise? I want to get a feel of, if I know the distribution from which I have sampled the data, I know everything about the data, about the context. I don't know. All I have is sample. All I have is the data, all right? Given set of data points, is there a way in which I can identify the PDF from which I got that particular, I have sampled that data from? That's a problem. And why do you do it? It finds applications in like n cases where the moment I can estimate the density, I can generate more samples. I have a generative model of what we call learning. If I can estimate class conditional densities, I know the posteriors and I can compute the posteriors. If I can estimate the posteriors, I have a classifier. So there are n applications for identification of densities. Yeah, P is basically like, it's a frequency count, essentially, Ravi teach. It turns out that, what do you call, in a binomial case, the parameter estimation, the best parameter estimation becomes, what do you call, the frequency, primarily like the trivial case. Yes, I'll repeat the maximum. Maximization is simple, Mukut. It's basically like the first order condition. I'll repeat the one. So I have an experiment, 11 times a coin is flipped. Each of this is a Bernoulli trial, 11 Bernoulli trials in a row, and I'm counting the number of successes. Success is a head turns up in an experiment, in a particular trial. And yeah, it's well represented by binomial distribution. Binomial distribution is a way to represent, all right? So, but I don't know the parameters of binomial distribution. So how do I find maximum likelihood estimation? Is I know the form of the distribution. I know that it's binomial distribution, but I don't know the parameters. How do I maximize this likelihood function? I know the likelihood function can be represented in terms of the parameter P, because it's a binomial distribution. I've got the, what do you call, the binomial distribution represented here. It's 11 to 6 p raised to 6, 1 minus p raised to 5. I mean, how do you, what is the logic behind it? See, like p raised to 6 times head appears and 1 minus p raised to 5, meaning 5 times head is not appearing, meaning the tail appearing. And in this experiment, if you have looked at, I am sure you must have looked at Bernoulli trial. Bernoulli trial is, there are only two outcomes. So p and 1 minus p becomes the probability varies for the success and the failure. So 1 minus p raised to 5 means that it failed 5 times, it succeeded 6 times, and you can actually choose these 6 successes in multiple ways, right? You can get a success in first 6 trials, you can get a success in last 6 trials, you can get success in alternative and then one more, whatever, right? You can get the 6 heads in different ways. That is 11. It's basically like the 11 choose 6. 11 choose 6 is, I mean, out of 11, how do you choose 6 successes, the 6 heads, 11 positions, right? Primarily, like, how do you choose those 6 heads in those positions? Is 11 choose 6. And then p raised to 6 is essentially representing the 6 successes, and 1 minus p raised to 5 is representing the 5 failures in that consecutive Bernoulli trials. All right. And how do you maximize the first order condition? Dou by dou p of p is your parameter. You maximize. You want to find the what do you call the parameters in such a way that which maximizes this. So maximizes this. What is this? This is basically the likelihood. So you want to find the parameters in such a way that the likelihood is maximized. How do you maximize this function? You can take the derivative with respect to the parameter, which is dou by dou p of the likelihood function L theta, right, or LP, and then you get it's first order condition, and then what do you do, right? So you get 11.6 in both sides, 11.26 in both sides. It's 11 factorial divided by 11 minus 6 factorial, 6 factorial. So that's immaterial because it comes in both sides. You find the derivative and you get this, right? 6p raised to 5 into it's simple algebra, computing dou L by dou p. Right? Does that answer your question? Why do you do it? It depends on. No, this is not. It's not. Yeah, that's how you estimate, Vishnu. That's how you estimate. We'll come to very similar contexts. It's essentially like when you estimate, you have discrete points. Even when you have a continuous distribution, the notion of assigning value to a point doesn't exist in the notion of a PDF. I mean, basically density. So you're dealing with discrete set of elements, and you want to estimate what do you call a continuous function, essentially. So you may end up like Vishnu. Does that answer questions? Yeah, it can be context of a density. I mean, even though like it may be an abuse of terminology. Yeah, they call it density estimation. Right, density. It can even be a PMF at times. Depends on like what sort of. So in our case, it's a PMF, right? I understand your question. You're calling density. It's essentially PMF. Vishnu is Namputiri. Are you there? Yes, it's an abuse of terminology. I completely agree. But that's how it is. They call it density estimation.
Excuse me, sir.
Yes.
So actually, here the condition has been given that there are 6 successful events in 11 independent trials, right?
That's all.
So basically, we are again finding out the same thing that p cap is 6 by 11, which has been given already. So I'm unable to understand.
No, it's not. It's not. Who gave you that?
P cap.
You have found that p cap happens to be the estimate of p cap will be 6 by 11. That's what you have proven, right? Nobody gave you that p cap is 6 by 11. We have from the calculation the maximum likelihood estimate of p cap is 6 by 11.
Sir, I'm unable to understand what does it mean exactly.
What does it mean exactly?
Yes.
It's the estimate of p cap. See, if you have got 11 trials, which is essentially in a binomial distribution, the number of successes divided by the number of trials is essentially like it will give you an estimate of the parameter. That's what it is. That's the meaning of it. So, for example, when you say mean, right, mean of a distribution, mean of a set of values, right? How do you find the arithmetic mean? Arithmetic mean of a set of values.
Sum of all the values divided by.
Why do you say that? I will say it's an expectation, provided every point is equally likely. Do you agree?
Yes, sir.
Expectation where every point is equally likely, you call it mean, and that's the definition of it. We are doing a very similar thing here. I don't know what P is. I've seen some experiments. Can I get a feel of P? And I have realized that P is nothing but the number of successes divided by the number of Bernoulli trials. You get it?
Yes,
that's what it is. That's what it is. We are realizing that this is the estimate.
Okay, sir.
That's what you get it, right?
Yeah, yes, sir.
You get. I mean, see, you have from the textbook. You have learned that P. This is how you compute P. How do you get that is what we have seen here.
Yes, I got it, sir. Thank you.
Okay. Any other questions? It's very simple, but you need to understand. Concept is very simple. I would say like, what do you call it? I mean, if you look at, that's one example that I wanted to say. Mean is nothing but expectation when. All right. Very similar to that. We'll get, these are trivial things looked at in a non-trivial fashion so that you understand what it means. Any other questions? Vishnu, good that you brought up that point, because it's, I mean, people keep say, the moment you say density, right, and point estimation of it doesn't make any sense. All right, people do that. All right, and that's the only way in which you can estimate, because you're working in a space where you have only discrete number of discrete set of values, and you need to estimate. Right, let's move on to the next example, probably. Right, this is what it is. Estimate of p cap would be number of success divided by number of trials. Let's go a little further. What I have done here, calculation of maximum likelihood estimate. It's also called MLE. MLE of an unknown model parameter theta would be the value of the model parameter that maximizes the likelihood. There is a little problem that sentence. The value of model parameters of is missing. The value of the model parameters that maximize the likelihood is called the maximum likelihood estimate. All right. How do you do an optimal estimation? We are looking at the theoretical aspect of it. We define L theta as the likelihood function over the observed data points. Vishnu, you will see this here. All right. We have only observed. We have a set of observed data points xk. All right, and we can represent the likelihood of xk being seen if theta is a parameter. That's called p of xk given theta. And I assume that these are IID, right, identical and independent samples. These are IID samples. So I can actually multiply, right? I have k of them. So pi over k, p xk by theta becomes my likelihood function. All right, this is a product. Better to work with a logarithm. So we normally in MLE go for natural log of the likelihood function. So L theta can be represented as natural logarithm of p xk, probability of xk given theta summed over k. All right, you just represent your likelihood function in natural log. Then you move on. What do you do? Now you have to apply the first order condition to maximize this log likelihood function. There is a gradient vector. In our case, we had only one parameter called p, which is we call as theta. But in the general case, there may be multiple parameters. So for example, you're going to see one here today. In the case of normal distribution, you have two parameters, the mu and the mean and the standard deviation, mu and sigma, right? We have got two parameters, right? So you get a gradient operator rather than you need a single dimensional gradient, right? You have a gradient operator. Determine theta, which maximize the log likelihood is our agenda, all right? So you find for the log likelihood function, which is L theta, you find the gradient and equate that to 0. Right. In our case, the log likelihood is L theta summed over k logarithm of p xk given theta. All right, logarithm of p xk given theta, and you apply the gradient over that sum. Right. Equate that to 0. That's a process. Let's look at this example. I want you to stare at this example for a moment, and then right. Estimate the probability p that individuals are infected with a certain kind of virus. It's again, let's assume that IID samples. Index is a number. I've got for 10 people, there is an infected case which is represented by 1 and the probability of finding of an infected person, that population is P, and which means that not infected is 1 minus P. So what is your likelihood function? LP would be P raised to 6, 1 minus P raised to 4. All right. So now we have, it's not, all right. This is what you see as data. All right. You find the log likelihood function. All right. Log likelihood function would be, so instead of, earlier we were not using log likelihood. The standard approach is go for a log likelihood, which primary purpose is reduce the computational overhead. All right. Represent the log likelihood. LP would be 6 log P plus 4 log 1 minus P. How do you maximize it? Dou LP by dou P. So you get that whatever dou by dou P of 6 ln P plus 4 ln 1 minus P, and you get 6 by P is equal to 4 by 1 minus P, and P will be 6 by 10, which is again the ratio, right? Ratio success to the number of trials. Success is finding somebody with a virus. Good. I've made this two toe examples to show you that the earlier case we were not using log likelihood, but the typical scenario is context is people use log likelihood estimation, and I've taken this example from the data from the web, and I've created the example so that it's a toy example where you understand what it means. Any questions? If you're okay with this example, we'll move on to the, so essentially the process is maximum likelihood estimate. The process is you represent the likelihood function, which is essentially capturing the probability of observing the given data, right? Provide the parameters are theta. So given theta, what will be the, how do you maximize the observed data, maximize the chance of seeing the observed data, right? You define the likelihood function over the observed data, which is, and you assume IID samples, I mean data is IID. So you can do a pi, instead of a pi, you can sum it up. If you take a natural log, you take the natural log, and then there may be multiple dimensions to the parameter vector. So the gradient operator would be a gradient vector. You apply the gradient over the log likelihood function and equate that to the first order condition for optimum, right? First order necessary condition for an optimum is this, right? And then you do this. So in our case also, in this case also, we know that we can represent the likelihood function and log likelihood take, and then we apply the first order necessary condition, and then you get the value of P, right, which happens to be success divided by number of trials, right? If you have understood this, let's go to a more realistic context. These were two examples. Normal distribution example. I know that I've taken a multivariate normal here. We have a prior information about the problem, normality, right? We know that the data comes from normal distribution. All right, this is the information we have, but we don't know the parameters. What are the parameters of a normal distribution? All right, and this is a multivariate normal. You see the form of a multivariate normal there. See that 1 by 2 pi d by 2 into, you have what do you call the covariance matrix, sigma and mu as the mean vector, right? So you have two parameters. The mean, it's a multivariate normal. So you have the mean vector and the covariance matrix, right? The covariance matrix is sigma, and you have mu as a mu. This is a case where you have you have a parameter. If the parameter is not singleton, you have n parameters to be identified. In our case, you have 2 parameters to be identified, and we know the form of the distribution, we know the structure of the distribution, right? Can we do maximum likelihood estimate of a normal distribution when you know that the data is from normal distribution, but I don't know what are the dimensions? I can say like I don't know the mean, but I know the variance, and primarily the covariance matrix is known to me. Or else I can say like, okay, I don't know both. All right, these are the 2 contexts that is typically available. All right, let's go to a simple example. That's the example of unknown mu. I don't know the mu. All right. So p of xi given mu, we assume that it comes from normal distribution. Samples are drawn from a multivariate normal. All right, it's taken from a multivariate normal. You also call it Gaussian. It's a multivariate normal. What is the first step in our MLE estimate? You find the likelihood, log likelihood function. What is your distribution? This is your distribution. How do you write the log likelihood? So, right. So you know that it's normal. You write ln pxk given mu would be minus half into, how do you do it? Minus half into that 2 pi d. There is a slight change. So I use a small d here. The previous one was small capital D recently. So d into half of xk minus mu into xk minus mu. Basically, like I just apply the logarithm there, and once I have it, what's the next step? I should find the gradient primarily like with respect to the parameter mu, right? I should find the gradient with respect to the parameter. So delta with respect to mu of that log likelihood would be, I can say like ln. If I look at it, I have mu is like I told you that unknown is only mu. All right. So sigma, rest of the things are fixed. So the first part will go off, and I'll get ln p. Right, ln p xk given mu, that is what I need to find. And if I get it, I get only the second part of that, minus half will so basically like xk minus mu, so that 2 will go off, 2 will cancel, and then you'll get xk minus mu, right? Sigma inverse into xk minus mu is what you get. All right, sigma inverse into xk minus, you get it from here. All right, you get it from here. This part will remain. Sigma inverse is differentiation. All right, so sigma inverse into xk minus mu, this will be equal to 0. That's the first order condition. Xk minus mu is equal to 0. All right, so which will, if you look at this, so sigma inverse is again like we presume that it's it's fixed, which means that summation over k xk minus mu is equal to 0. Right, so n times mu added, mu is what you find, right? Mu is a mean. N times mu is equal to summation over xk. All right, and yeah. So what you do is, and the algebra is also specified. It's basically like sigma inverse is constant, so you can multiply it by sigma and you get rid of it. It's one side is 0. So you can cancel it. So you get mu is equal to 1 by n of xk, arithmetic average of the sample of the training samples would be the mean. Right? If you have got points taken from a multivariate normal distribution and you know that only the mean is not known to me, the mean can be estimated as, we realize that the mean can be estimated as the arithmetic average of the samples of the training data. All right, that's what the realization is. And this particular part of the content I've taken from the book by Duda and Hart. Duda and Hart explains this. It just gives you these equations. All right, so maximum likelihood estimate for a multivariate normal distribution is happening is computed like this. You take you know the form of the distribution, and we assume that only the unknown parameter is mu. You write once you know the distribution, you write the log likelihood function and take the gradient with respect to the unknown parameter and equate that to 0. What you get will be an estimate of the unknown parameter mu here. I know that this is little math intensive for those who are not with a proper math. This would look little difficult, but I urge you to go back, look at it. All right, it's straightforward algebra. It's all you do is you need to know the form of normal distribution, and then you write the log and find the gradient and equate the gradient to 0. You get this. All right, this is little more complicated. All right, Gaussian case, unknown mu and sigma. You got two parameters, theta 1 and theta 2. Right, mu is theta 1. I don't know both mean and the standard deviation. Right, how do you do this? Right, I'll go by the same procedure. What is that procedure? I write the log likelihood minus half ln 2 pi theta 2. So same thing. I'll take minus half ln theta 2 pi 2. Same thing. I get this here. Minus 1 by 2 theta 2. Here I had, all right, 1 by, I know this part, all right, 1 by, see, this is sigma inverse into k minus mu. See, so what I do is here it's 1 by 2 theta 2. Theta 2 is sigma xk minus theta 1 the whole square. It's, since I got exponential here, right? I got an exponential here. So 1 by 2 into xk minus theta 1 the whole square, and my gradient vector would be like, I've got two dimensions to the parameter vector now, theta 1 and theta 2, theta 1 being the mean and theta 2 being the variance. Right, what do? I find the I apply the gradient vector over the log likelihood. So from the first one, I'm differentiating with respect to theta 1. With respect to theta 1, if I differentiate this, the first part will be gone and second part will be 1 by theta 2 into xk minus theta 1. That 2 will go off, is equal to 0, and I get equivalently 1 by 2 theta 2 plus xk minus theta 1 the whole square by 2 theta. So basically 1 by theta 2 will be 1 by x minus 1 by x square. So you get that 1 by 2 theta 2 square is equal to 0, and if I so this is for a single point. All right, this is for a single point. I do it for a single point. I can I've got n points here. So what I do, I sum it over. Right, I sum it over the entire k points or n points. All right, and I get that gradient equated to 0, the first order conditions, and I'll get a very similar equation. Mu would be equal to xk minus n, and the variance would be equal to xk minus mu the whole square divided by n. So essentially, like you get trivial estimates. Right. All I want to say is this is, I know, like this is a little scary if you're not very good in, if you're not work with little of mathematics. But I urge you to go back, look at these slides, and you can come back to me if there is any concern over here. And this is simple algebra. So let me do a recap. What do you do in maximum likelihood estimate? Maximum likelihood estimate is all about a context where you know the form of the distribution, but you don't know the parameters of the distribution. What do you do here? You can represent, you know the form of the distribution. You can represent the likelihood of data with respect to the parameter, right? You represent the likelihood function. Typically, the likelihood is represented in a logarithmic form for convenience. All right, you've got, which means that, and you assume that your data points are IID, which says that you can multiply the corresponding likelihood functions. But when you take logarithm, the product becomes summation. So you get summed over all the points available, the log likelihood, right? Once you get the log likelihood, what do you do? you have to find the parameter. You have to find the parameters in such a way that the log likelihood is maximized. So how do you maximize this function? You apply the first order necessary condition, right? A dou L is the likelihood, dou L by dou theta. Theta is your parameter, right? If a parameter is a singleton, it's a single parameter, you get the normal one, and if you have otherwise, you'll have a grading vector, right? So dou L by dou theta is equal to 0 is what you is your first order necessary condition, and then to maximize the likelihood function, log likelihood function, and from that you can get what will be you'll get an estimate of theta, right? This is the basic idea of maximum likelihood estimation. All right, all I want you to do is I'm just stopping MLE here, and we may have to do a little more exercise maybe later point in time, but I want to give you 2 assignments here. One is compute the maximum likelihood estimate in a case where the distribution is exponential. For exponential distribution, how do you compute maximum likelihood estimation? Exponential distribution, one more, maximum likelihood estimate for a univariate normal. What I've shown you is a multivariate normal, right? It's a multivariate normal. So 2 exercises to be completed. One is take a piece of paper, do maximum likelihood estimation for exponential distribution. You can take the context of an exponential distribution and show. I've shown you examples for a binomial distribution. I've shown you example for a toy data, right? Without, let's assume that it's again like it's what do you call, your data points are given, discrete data points are given, and I've given you an example for a multivariate normal. Do MLE for exponential distribution and univariate normal. MLE for exponential distribution and univariate normal, right? Do it. The steps are simple. MLE is a context where you know the form of the distribution, you find the you write the likelihood function, you write the log likelihood function, maximize the log likelihood function in such a way that your parameters maximize the log likelihood function, which essentially computes the parameters in such a way that the likelihood of your data is maximized, right? The maximum likely, hence the name maximum likelihood estimate the parameters in such a way that the likelihood of the data observed is maximum likelihood estimate, maximum likelihood of the data, right? That's what it is. The estimate in such a way that the maximum likelihood of the data observed is the norm, right? That's called maximum likelihood estimate. But if there are any specific questions, we can discuss it here. I see some chat. Slight confusion to me here. Taking grade operation. Grade is basically after taking the gradient, we get a vector quantity. No, we are getting a vector quantity here. We are getting a vector quantity here. Just look at here, Vishnu. A vector. Look at the last one. We have a vector. I've not represented in a vector form. That's it. You got 2 elements. Vishnu, does that, just look at that slides carefully. You got a vector. You have a vector there. You don't have a scalar. You have a vector. I've represented that in a, what do you call it, more convenient way to understand. That's it. It's a vector. After taking that vector quantity here, we're taking grad 2 with respect to theta. Theta is a vector. It's essentially like theta is primarily like it has 2 dimensions, theta 1 and theta 2 in the case of a multivariate normal. And unknown assumption was unknown mean and unknown variance. See, I don't understand what you meant by geometric interpretation, but it's essentially like you're doing estimations. And a geometric interpretation doesn't make any sense in estimations, right? Good. I think I'll stop recording for this particular step.